For this one, we're going to go over the Gizmo, that is the distance time and velocity time graphs. When you first open this Gizmo, it's going to look a lot like the Gizmo that we did in the past with just the distance time graphs. But if you look closely, there is a tab labeled velocity time graph. So you'll be able to compare your distance time graph to your velocity time graph. Oops. So in the first question, it's a prior knowledge question. It says that Dora runs 1 lap around the track, finishing where she started, and Clark runs 100-meter dash along a straight side of the track. So Dora's going to run all the way around the track, and Clark is just going to run the 100-meter dash. So which runner traveled a greater distance? For distance, Dora ran 400 meters and Clark ran 100 meters. So Dora ran farther. Which runner had a greater change in position? So that's talking about displacement. Displacement, okay, change in position. Displacement. So Dora, because she started and stopped in the same spot, her displacement is actually 0. Whereas Clark, because he ran in a straight line on the straight side of the track, his displacement and his distance are both 100 meters. So Clark actually has a greater change in position compared to Dora, even though he didn't run as far. This Gizmo includes distance time graphs and adds 2 new ones, velocity time graph and distance traveled versus time graph. The graph shown below shows a runner's position over time. This is most commonly called a position time graph. So you'll hear me say distance time and position time graph. I'm talking about the same kind of graph here. So we're going to compare the 2 runners. So we have the red line here and then the blue line here. So in what 2 ways are these runners' motions going to be different? And I'm not even going to switch to the Gizmo here because we should already know this one based on what we've learned so far about distance time graphs. So because the runners, the slopes of the lines, one goes up and one goes down, we know that the runners are going in different directions. We know that the red runner, because his slope is going up, is moving to the right or in the positive direction, and the blue runner, his slope is negative, so he's running in the negative direction or to the left. And then also you can see that the red line is steeper than the blue line. So the red line, the red runner covers 40 meters in 4 seconds, and the blue runner only covers 20 meters in 4 seconds. So the red runner is going faster, so they're going at different speeds, where the red runner is faster, because his line is steeper. Okay, in the Gizmo, make a position time graph for runner 1, a distance time graph. They want you to have 1 major change in speed and 1 major change in direction. And you need to have your points to 5. Now I'll go ahead and make a random graph so that we can study the, so we can fill in the chart together so you can see how it's done. But you should have a different graph for your assignment. Everybody's graph should look different here, since it was not assigned to you. So I'll just go ahead and draw a graph. So let's start at 0. We need to have a major change in speed. So why don't we have a pretty flat line to start? And then we'll get steeper. We'll have a really steep line. And then we need to have a change in direction. So we can go ahead and make our line go down. Let me try that again. There we go. So there we've got our change in speed. So we're going slow and then fast. And here we've got our change in direction. We were going up and then we're going down. So where was the runner for each second? Based on your graph, fill in all except the final column. We'll do that in the next step. Number 3 down here will tell us how to fill in this column here. Label any numbers with units. That's important here. So after the first second, from 0 to 1 seconds, at the position at the end of the interval, so they go by 2, so we were at 2, 4. So we were at 4 meters at the end of the interval. And we started at 0, so that means that the distance we moved was also 4 meters. Our slope is positive, so we were going away from start. So you can just label these as positive and negative. So away from start is positive, and coming back towards the start is negative. Okay, from 1 to 2 seconds, we moved from here to here. So at the end of the time interval, we were at 30. And we moved from the 4 to the 30, so that's going to be 26 meters, the distance we moved, and we were going in the positive direction. Okay, from 2 to 3 seconds, we went from the 30 to the 20. So we were at the 20 at the end of the time interval, and we moved 10 meters, but we went backwards. And then for the last second, we went from the 20 to the 10. So we ended at the 10 meter. We went a total of 10 meters, and we were going negative. So from 20 to 10 is 10 meters. Okay, now down here it tells us to calculate the velocity for each time interval. First, calculate the speed of the runner in that interval. Speed is distance divided by time. So this is pretty easy to calculate because our time is 1 second for each interval. So you're going to do the distance divided by 1 second. And then it says if the direction is away from start, velocity is positive. If the direction is toward start, velocity is negative. So for our first one, we're going to do 4 divided by 1, and it's going to be positive. So it's going to be positive 4 meters per second. For the next one, it's going to be 26 divided by 1, and it's going to be positive. So positive 26 meters per second. And then the last two are both the same speed. We move the same amount of distance in 1 second each. So they're both going to be 10 meters per second, and they're both going to be negative. Those were our velocities for each of the seconds for this graph here. When this runner is running towards start, so in the negative direction, to the left, what does his position time graph look like? When you're moving to the left, you have a negative slope. So up here, that's this section where the runner was moving to the left. The steepness of the graph is the slope. To find the slope of a line, divide the change in the y value, the rise, divided by the change in the x value, the run. Like velocity, slope can be positive, 0, or negative. On a position time graph or a distance time graph, the velocity is the slope. Slope is velocity. So the slower your velocity, the more gentle your slope is going to be. If you're moving faster, you're going to have a steeper slope. So on the left side of the gizmo, select the Velocity Time Graph tab. Use the green probes to compare the velocity time graph to the position time graph. And we need to look and see how does a velocity time graph show that a runner is moving fast, and how does a velocity time graph show that the runner is moving away from start. So that's going to be to the right in the positive direction. So here is our distance time graph. And here's our velocity time graph. So let's watch the runner go one more time. So the section where our runner was going fast is where our line is the steepest. So that's going to be between 1 and 2 seconds is where our runner was going the fastest. And you can see that on the velocity time graph tab on the left, that value is much higher. It's a flat line, but it's higher up than the rest of the graph, and it's in the positive section. So you'll notice from 0 to 2 seconds are on the velocity time graph on the left, the straight lines are above the x-axis, where our runner's moving forwards, and then where our runner's moving backwards, that velocity time graph is below the x-axis in the negative. So here he's negative, so it's negative values. Here it's positive, so positive values. Okay, slow for the first second, so you can see how close that line is to the x-axis. It's a very low value. And then for this section, it's very fast, so it's a much higher value. Okay, so the faster the velocity, the larger the value. And when they're going away from start in the positive direction, the velocity values are positive on the y-axis, so they are above 0 on the x-axis. Looking at this graph, they want you to sketch the velocity time graph. So remember that for a distance time graph, the slope is the velocity. So that's what we're going to be graphing on the velocity time graph. So we need to do the rise over the run. We need to find the slope. For our first part of the graph, it's going down. So our rise is going to be negative. So we're going from 40 to 0. So our rise is going to be negative 40. Our run is 2 seconds. So 40 divided by 2. That's going to be negative 20. So we're going to zoom in on our velocity graph. We're going to have a straight, flat line at negative 20 for the first 2 seconds. For the second part of the graph, our rise is now positive. We're going up. So we're going to go from 0 up to 30, and our run will be 2. So positive 30 over 2. 30 divided by 2 is 15. The lines go by tens, so you need to put it in between the 10 and the 20. And then you'll just connect your 2 with a vertical. Okay, so that is your velocity time graph. How does a velocity time graph show that a runner is moving towards start? So this is to the left. Well, the values are going to be negative. So if you look here, we were going down, we were going to the left for that section, and you'll notice here that the values are below the x-axis. The values are negative on the y-axis. So for this question, we want to look at our 2 lines here on our position time graph. We have 2 lines, we have a red and a blue line. And notice that they're both going together. So we would call these lines parallel. These are parallel lines. So that means that they have the same slope and they go in the same direction. So they're the same distance apart, and they stay that way. They stay very proportional. They're parallel lines. What's different is the starting point and the ending point. They stay 10 meters apart the whole time. So their starting point and their ending points are different. What that means for the velocity time graph is, because the slopes are the same, because the lines are parallel, that means that their velocity time graph will actually overlap. They will share a velocity time graph. It will be the same for both. So let's go ahead and use the Gizmo to set this up and just to check. All right, so there's the runners. Let's watch them run. Oh, it's from the beginning. Okay, one more time. So they run together. They're in sync. They run forwards and backwards at the same rate. So if we look at their velocity time graph, you can see that the lines overlap. We're only seeing one line. But if I move the red one a little bit, you can see that it is, in fact, underneath the blue line. Okay? So they share a velocity time graph. So let's go ahead and draw that. So their slopes are positive 15 and negative 10. And just connect them with a vertical. So this is going to be the same for both blue and red because they're parallel. Okay? So they only have the same velocity time graph if they have the same slope and if they're going in the same direction. But notice that this graph does not show us anything about the starting position or the ending position. That stuff is left off of this graph. We will not be able to figure out their exact positions from a velocity time graph alone. 10, you can make any graph you want, so you just need to do that one on your own. You make any position time graph you want for both of your runners, and then you will sketch the velocity time graph from the Gizmo. So what we just answered, though, was the next two questions. Compare the velocity time graphs to their related position time graphs, which is the same thing as a distance time graph. When do two different position time graphs have matching velocity time graphs? And we said that was when they have the same slope and the same direction, and the lines are parallel. What's missing is the starting and the ending positions. We cannot tell that from a velocity time graph. When you have a curved line on your position time graph, that means that you have acceleration. Your velocity is changing over time. So for example, for this line, we're moving in the positive direction because we're going away from the starting point. We're going away from 0. And the slope is increasing. It's getting steeper and steeper as you move away from 0. So the velocity is increasing as you move away. So that means you have a positive acceleration. You've got a positive acceleration because it's curving upwards, and you're speeding up because your velocity is increasing as you move. Okay. So our line is going to look something like this, where your velocity is increasing over time. So no longer a flat line. And that's not perfect. I didn't go through and calculate the slope for each second, but it's just an estimation that your velocity is going to be increasing over time. For this graph, you've got to fill in the blanks. The runner will run blank meters in the first 2 seconds. So in the first 2 seconds, we're going to go from 0 up to 40. So we're going to go 40 meters in 2 seconds. Well, to figure out that velocity, that's pretty easy. We're just going to do the displacement divided by the time. So we went a positive 40 meters over 2 seconds. So that's going to be 40 divided by 2. Or positive 20 meters per second. And the direction is to the right or away from start. Then for the next 2 seconds, he will run how many meters? So he's going to run from the 40 down to the 30. So 40 down to 30. So that's 10 meters in the next 2 seconds. With the velocity of, well, it was negative 10 meters because we ran backwards. We ran to the left. The slope is going down. So negative 10 divided by 2 for the velocity is going to be negative 5. Negative 5 meters per second. And the direction will be back to start, to the left. So we'll say towards start. 2 students, Gina and Walter, are discussing the runner whose graph is shown above. Gina says the runner moved more than 40 meters, and Walter says the runner moved less than 40 meters. Who is right and why? So it depends on what they're specifically talking about. It says they moved, but we know there's different kinds of motion now. We can look at the distance or we can look at the displacement. So Gina could be right if we were talking about the distance. So we know that the runner moved 40 meters in the first 2 seconds and 10 meters in the next 2 seconds. If we combine those, the distance is 50 meters. But Walter says that he moved less than 40 meters. Well, if we looked at the displacement, which as you remember, you only look at the first point and the last point. So the displacement is positive 30 meters. Okay, that's the displacement from 0 to 30. Okay, so they're both right. It just depends on what you're talking about. So whichever one you chose there, just make sure you use the correct explanation. So Gina's right if you use the word distance. Walter's right if you use the word displacement. And so we've actually answered the next question by doing that. So the distance traveled was 50 meters, and the displacement was positive 30 meters. In the Gizmo, create a position time graph of a runner with these characteristics. Travels a distance of 60 meters in 4 seconds and has a displacement of 10 meters. Now this is kind of tricky to do. So I will go ahead and do this. We want to turn off the runner 2. Now for the displacement, the easiest thing to do is to start at 0. And it says you want to have a displacement of positive 10. So I'm going to move my last point down to plus 10. So if I start at 0 and I end at 10, that's a displacement of positive 10. They have this handy dandy distance traveled tab. So at 4 seconds, we want to have gone 60 meters. So I'm just going to drag the center dot down until I get to 60 meters. Oops, right there. Okay, so my dots are 0, 0, 2, and 35, and then 4 and 10 are my 3 dots. So there, he's gone 60 meters in 4 seconds, and the displacement was 10 positive meters. Dot there, dot there. There you go. What is the runner's average speed over all 4 seconds? Remember that speed is distance divided by time. And the distance was, they told us right here, 60 meters over 4 seconds. So 60 divided by 4 is 15. So 15 meters per second. The velocity, we're going to use the displacement. So that needs to be positive or negative. And we're going to do the velocity for the first 2 seconds and the velocity for the last 2 seconds. So for the first 2 seconds, my displacement was, we went from 0 to positive 35. Okay, so we went up 35 meters. So displacement divided by time is positive 35 divided by 2, because we're splitting it in half. So that's going to be positive 17.5 meters per second. For the second part of the graph, we are going down. So we're going in the negative direction. So our displacement here is going to be negative. So we're going from 35 down to 10. So that's going to be negative 25 for the displacement. So displacement divided by time is going to be negative 25, but still 2 seconds, over 2 seconds. So that's going to be negative 12.5 meters per second. And for our last graph, I'm going to actually add a question to this, and we're going to calculate the average velocity in addition to the distance traveled, the displacement, and the average speed. So for this graph, to find the distance traveled, we need to look at each segment and find out how much distance each segment was, and then add them all together. So for the first one, we went from 0 up to 30. So that's easy. We went 30 meters. Then we went from 30 down to 10. So that's going to be 20 meters. From 10 to 40 is 30 meters. And from 40 down to 20 is 20 meters. So that's pretty easy to add up. So 30 plus 20 is 50. You're going to do that again. So then you get 50 plus 50, and you get 100 meters. The displacement, we only look at the first point and the last point. So if we start at 0 and we end at 20, that's going to be a displacement of positive 20 meters. The average speed, we want to use the distance divided by the time. So we're going to do 100 meters divided by 4 seconds. So that's going to be 25 meters per second. And for the velocity, we're going to use the displacement divided by the time. So the velocity is going to be positive 20 meters divided by 4 seconds. And that's going to give us a velocity of positive 5 meters per second. So there you go. That's the Gizmo. Message me if you have any